Okay, our topic in this lecture is discrete Fourier transform, which we abbreviate as DFT, and we have abbreviated the discrete time Fourier transform as simply Dtft. Okay, so in the last lectures, couple of lectures, we considered the question of convergence or existence of the DTFT, and we said that absolute summability of the sequence is a sufficient condition, not a necessary condition. Similarly, square summability of a sequence is also a sufficient condition. There are sequences which are square summable but not absolutely summable, and the example that we took was 1 over n times u of n minus 1. Then we said that there are sequences which are neither square summable nor absolutely summable, but their DTFT can be defined in terms of the analog delta function, which we denoted by del of omega. Here the argument is not in the time domain, it is in the frequency domain, it is continuous, frequency and continuous. So, that is why it is called the analog delta function. Since it is continuous, it is called the analog delta function. As an example, we took the DTFT of e to the j omega naught n, and we showed that it is 2 pi times summation of del of omega minus omega naught plus 2 pi k, okay, where k goes from minus infinity to plus infinity. We also gave you the basic table of DTFT, where the basic functions are del of n, then u of n, and then we considered e to the j omega naught n, and then alpha times u of n. If you know these four functions, okay, if you know the DTFT of these four functions, then you can find almost all DTFTs. Okay, so you can find out almost all DTFTs of all familiar sequences. Okay, and then we took the example of upsampler. Okay, and we showed that the spectrum gets compressed up. And I would suggest that you carry out the example of downsampler, and also downsampler, and find out what happens to its spectrum. Okay, and then we took an example of inverse DTFT, which does not require integration. A bit of thought reveals that it can be done very simply by expanding cosine or sine in terms of Euler relations. Using that you can expand, then you will get the inverse DTFT. And then we discussed some properties of DTFT, such as linearity, time shift, then frequency shift, then convolution, modulation, right. Modulation is multiplication in the time domain. Multiplication in the time domain. Okay, and finally we discussed Parseval's relation, which has an interpretation in terms of energy. That is, energy in the time domain is equal to energy in the frequency domain. And then we talked about symmetry relations. Okay, one symmetry relation is that if x of n has dtft of x of e to the j omega, then we showed that x of minus n has the dtft of x of e to the minus j omega. Okay, and similarly x conjugate of n is the pair of capital X conjugate of e to the minus j omega. Okay, and then if x of n is complex, then real part of x of n is the Fourier pair of 1 over 2 x of e to the j omega plus x conjugate of e to the minus j omega. Similarly, if you want to find out the imaginary part of x of n, this is equal to 1 by 2j capital X of e to the j omega minus capital X conjugate of e to the minus j omega. Okay, there are other symmetry relations which we want to mention casually because they are obvious. If x of n has the dtft of x of e to the j omega, which is of the form real part plus j times imaginary part, then the even part of x of n, that is the dtft, would be the real part of x of r. If you want to even part of x of n, if you take the dtft, then this would be equal to xr. Similarly, if you want to find the dtft of odd part of x of n, and that would be equal to what? J times the imaginary part of x of e to the j omega. Okay. And we also said the real part is even, imaginary part is odd, the magnitude is even, and the angle is odd. Okay, so these are all repetition. So repetition is beneficial for learning to a certain extent, but if it is repeated many times, then it loses its significance. Okay, and that brings us to the DFT, discrete Fourier transform. Okay. So the next topic that we would like to discuss is DFT, discrete Fourier transform. Discrete Fourier transform is different from discrete time Fourier transform. So to understand the concept of DFT, let us consider a sequence x of n. And one more important point I would like to tell you, that DFT holds only for very important point, sequences of finite length. The length must be finite. Okay, if the length is very big, or no, I can't say very big. If the length is infinite, then you cannot take the DFT. Okay, so x of n, the length is 0 to n minus 1. So very important point, this is finite length sequences. Then how do you find out the DTFT of this discrete time Fourier transform? Capital X of e to the j omega is equal to summation of x of n e to the minus j omega n, where n goes from minus infinity to plus infinity. Now, as I said, in this DTFT, it holds only for finite length. Therefore, in this summation, I am going to change the limit from infinite length to finite length. Let us say my sequence starts at 0 and ends at, I said n, capital N. Therefore, the upper limit must be n minus 1. Then x of n e to the minus j omega n. Now you expand this, you will get x of 0 plus x of 1 e to the minus j omega plus x of 2 e to the minus j times 2 omega plus dot 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 plus x of capital N minus 1 e to the minus j omega within a bracket n minus 1. Now the left hand side you have x of e to the j omega. Now look at this expression carefully. Okay, it is a polynomial in e to the j omega. Look at here, I have e to the j minus j omega, e to the minus j 2 omega, e to the minus j omega times n minus 1. Here also I have e to the j omega times 0. Therefore, this is a polynomial in e to the j omega. Okay. Therefore, this x of e to the j omega, is completely specified if this n number of coefficients are specified. What are these n number of coefficients? These guys. X of 0 is one coefficient, x of 1 is another coefficient, x of 2 is another coefficient, x of n minus 1 is another coefficient. Therefore, we have capital N number of coefficients. Okay. How many coefficients? Capital N number of coefficients. So, if I know this capital N number of coefficients, then I can completely specify what my x of e to the j omega is. So, a polynomial is specified in terms of its coefficients. So, for capital x of e to the j omega, which is a continuous function of omega. Continuous function of omega. It suffices to specify capital N number of constants. Okay. And here the constants are this. What are those constants? X of 0, x of 1 up to x of capital N minus 1. These constants can be in the time domain or they can also be in the frequency domain, but here the constants are in the time domain, x of 0, x of 1, like that. So, now the thing is, constants can be either in the time domain or in the frequency domain. So, in the time domain it is already given, okay, x of 0, x of 1, x of 2, like this, x of capital N minus 1. In the frequency domain, the variable is omega. Okay, it is a polynomial. So, the variable is omega. So, the constants are capital X of 0, capital X of 1, like this, capital X of N minus 1. So, if I take a capital X of e to the j omega and sample it, okay, give to the sampler, sample it at a n number of distinct points, that should be good enough. Capital N places of information are required to specify this x of e to the j omega. This information can be in the time domain, like small x of 0, small x of 1, dot dot dot, small x of n minus 1, or this information can also be in the frequency domain, like capital X of 0, capital X of 1, dot dot dot, capital X of n minus 1. Therefore, what it says is, I can sample in the frequency domain. In other words, if I sample capital X of e to the j omega at a capital N number of points, this n number of points are distinct points, then we have n independent pieces of information. Once you do sampling, you will get n independent pieces of information. In the time domain also we have no n independent of pieces of information, and these n independent pieces of information should be enough. Okay, that should satisfy. So, what we do is, instead of time domain constants x of 0, small x of 0, x of 1, small x of 1, small x of n minus 1, we take in the frequency domain guy, this guy. So let me modify this e to the j omega k, where k can be 0, 1, 2 up to n minus 1. So instead of taking the samples in the time domain, so in the time domain, what is the variable here? N is equal to 0, 1, 2 like this. In the frequency domain, my variable is omega, that variable is multiplied by k, where k runs from 0, 1, 2 up to n minus 1. Okay, therefore, there must be capital N number of distinct points in the W domain, capital N number of distinct points in the W domain. W domain means frequency domain, that's it. Okay, so that should completely, this n number of distinct points completely, okay, this n number of distinct points in the W domain must completely specify capital X of e to the j omega. That is, a part of the information is adequate to construct the full information. Usually this is not possible from only a few parts, one cannot construct the whole, alright. So if I give you pieces of information like 2 or 3 pieces, it requires a lot of research to find out what that furniture is. Okay, if somebody comes and gives you pieces of furniture, okay, 2 or 3 pieces of furniture, then it requires a lot of research to find out what that total furniture is. I simply give you 2 types of suppose if I simply give you 2 legs of a chair, this is also form a plank or some other furnitures, but it is possible in this constants. Okay, but here it is possible to construct from this constants, because the function itself has only capital N pieces of independent information. If you take the original, here this itself has, originally it has itself has n number of independent information. So if somebody comes and gives you the information in the frequency domain, then that also enough. The information about omega, here omega is a variable, then x of 0 plus x of 1 times e to the j omega plus x of 2 times e to the j times 2 omega. Now where is the information? Information is in x of 1, x of 0 and x of 2. This guy doesn't have any information. Okay, it does not have any information. It's a polynomial. Only the coefficient has. Therefore, this is not a information. E to the j omega is not a information. Information is only in terms of the constants. What are those constants? X of 0, x of 1, x of 2 and so on and so forth. Therefore, this x of 0, x of 1, x of 2 forms the basis of defining the Dtft. Therefore, the sampling at k number of points can be x of e to the j omega is, if you give it to the sampler, then you are taking e to the j omega k. Okay, so how many samples are you taking? K number of samples. So this sampler can be uniform or non-uniform, but we are going to consider uniform sampling. Okay, so uniform sampling is preferred because this keeps our life simple. So what we do is, okay, to understand this, let us construct a circle like this, construct a circle, okay, and omega goes in the anti-clockwise direction, omega increases in the anti-clockwise direction. So it goes from 0 to pi by 2 to pi to 3 pi by 2 to again 0. That is or 2 pi. So why do we consider omega between 0 and 2 pi? Why do we need to consider this range? Because we said capital X e to the j omega dtft is periodic with period 2 pi. Okay, so within one period, if I take capital N number of samples, then I should take samples at every 2 pi by n. See, I need how many samples? Capital N number of samples. But my length is 0 to 2 pi. How can I take? I am going to employ uniform sampling. So the first sample I will take by 2 pi by 1. Sorry, let me take the first sample at 0th itself. Second sample at 2 pi by 1. Third sample 2 pi by 2 pi by n times 2. Like that, keep on increase. And the last sample would be n minus 1th sample. 2 pi by n times n minus 1th sample. So I have 0th sample, first sample, second sample, third sample, and so on up to n minus 1th sample, 1th sample. Okay, so within one period, if I take capital N number of samples, then I should take samples at every 2 pi by n. The range 2 pi we divide into n equal intervals. Okay, so this 0 to 2 pi is divided into n equal intervals. Okay, this is x of 0, first is okay, capital X of 0, and this line is 0 degree or 2 pi degree, and the second point is 2 pi by capital N, and this we call x of 1, and the third sample is 2 pi by capital N times 2. So this is x of 2, sorry, yes, like that you keep on do it. And the last sample is n minus 1th sample, n minus first sample. So this sampling time is 2 pi by capital N times n minus 1. Okay, so this will be my first sample. I call this sample capital X of 0, and then another you get at 2 pi by n, I get x of 1, and then so on so forth. So I come up to 2 pi by n times n minus 1, and therefore I will get a which sample? This is equal to capital X of n minus 1. So this picture defines DFT, discrete Fourier transform. In other words, our definition of DFT is x of k. Okay, and this symbol is used for x of e to the j 2 pi k and divided by n. Okay, and what is this 2 pi by n? This 2 pi by n is the basic interval of the sampling. So okay, from between two consecutive samples, the interval length is 2 pi by capital N, and then you multiply by k, okay, k times that. So this is what we are defining for DFT. Therefore x of k, this is a notation for DFT. Okay, for DTFT we set x of e to the j omega because it is a polynomial in e to the j omega, and here it is in terms of k, therefore I wrote capital X of small k. This is defined as summation of DFT of discrete Fourier transform of x of n. So how do you get DFT? By sampling the x of e to the j omega. You take x of e to the j omega, sample it with periodic intervals and k. Okay, so we know x of e to the j omega by definition. What is that? Summation of x of n e to the minus j omega n. Now you replace this omega by omega times 2 pi by capital N times k. Therefore, you will get this one. So, this is going to be summation of x of n, don't disturb, e to the minus j. Omega is replaced by omega times 2 pi by capital N times small k. And of course, the limit is from minus infinity to plus infinity n. So, this is the definition of DFT, discrete Fourier transform. Okay, and this x of k is the Dtft sampled at these values. So, instead of e to the minus j omega n, I will put this guy, where n goes from 0 to n minus 1, because I am sorry, I am really sorry. Why did I put this one? This is wrong. Okay, I did a blunder. Okay, so now I need to put the limit n is equal to 0 to n minus 1, because we assumed x of n is of finite length. Therefore, x of k has to be computed for k is equal to 0, k is equal to 1 up to n minus 1. So, the sequence x of n, which is of finite length, and the sequence x of k, which is also of the same length. So, x of n is of the length of 0 to n minus 1. Its DFT, capital X of small k, is also of the same length n minus 1. Okay, and here the variable is k, and here the variable is n. Therefore, this x of n and x of k form 1-to-1 transform pair. Okay, so they are 1-to-1 transformation. Okay, so it's a finite length sequence. Let me put like this under braces. Now you can ask me a question, why is it 1-to-1? It can be shown by taking the inverse discrete Fourier transform of x of k is equal to x of n. Therefore, this x of n and x of k form the 1-to-1 transform pair. Okay, and this inverse DFT is given by let us say 1 over n summation of capital X of small k e to the plus j2 pi by one second, I did a mistake. I am sorry, somewhere I did a mistake. I am really sorry. This omega will not consider. The moment you do the sampling, this omega is, you are sampling right at discrete points, you are taking the value. I am really sorry, I did nonsense. Okay, you are taking samples, so the k is a variable, and here the sampling interval is 2 pi by n. So, therefore, omega is replaced by 2 pi by n here. So, this omega will not come, and this omega also will not come. I am sorry about that. Okay. So, this omega will not come, a to the minus j 2 pi by capital N times k. So, 2 pi by capital N times k, and the summation variable is from 0 to k, and k runs from 0 and goes up to n. Let me call this is equation number 2, and DFT we already defined. this is x of n, this is your IDFT, and DFT we already defined, right? X of k is equal to summation of x of n e to the j 2 pi by capital N times and kn. And here also I forgot to put n. Let's say this is equation number 1. Okay, now equation 2 has to be computed for n is equal to 0 to n minus 1. You first evaluate, substitute k this value, simplify the summation, and then substitute n value. So equation 2 is a matter of equation 1 is not a matter of definition. Okay, equation 1 is a equation 1 is a matter of definition, but equation 2 is not a matter of definition. Equation 2 follows from DFT, or if equation 1 is a relationship which is given, then equation 1 will follow. So this is a one-to-one transformation, and therefore going either in the forward direction or the reverse direction should suffice. So in the literature, for historical reasons, the quantity e to the minus j 2 pi by n is usually given this symbol capital W and suffix capital N. It is a bit of unfortunate that the negative sign goes here. Negative sign is associated with the Wn. But this is how it has gone in the literature, starting with the days of Cooley and Tukey. 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 Okay, so the point is, you take capital X of e to the j omega and take capital N number of samples, so in the omega axis. So each sample interval is 2 pi because we are going to employ uniform sampling. Okay, therefore this omega becomes 2 pi by capital N times small k. So like this you are doing the sampling. So omega is sampled, you are taking capital N number of samples. Therefore the sample width is 2 consecutive sample durations 2 pi by n, and it's a running variable k. So replace omega by 2 pi by capital N times small k. Now how will the equation 1 and 2 vary? By using this notation W suffix n. Your x of k is equal to summation of x of n, then Wn and Kn. Okay, so this is DFT. Small x of n is equal to 1 over n summation of x of k Wn minus Kn. Here n is equal to 0, 1 up to n minus 1. In this equation k is equal to 0, 1 up to n minus 1. So this is a complete description of a finite length sequence, either in the time domain or in the frequency domain. Now important point to note down. Okay, now in x of k, if you look at this equation, x of k, if I increment the small k by 2 pi or by n plus k, what is going to happen? Does it change? No. I have x of k. Now the question is, what is the value of k plus capital N? That is a question. Okay, x of k, we know the definition. X of k is equal to summation of n is equal to 0 to n minus 1 x of n e to the minus j 2 pi by capital N kn. Right? Now replace k by k plus capital N. X of k is equal to x of k plus capital N, which is summation of x of n e to the minus j 2 pi by n. You put small n here and k plus capital N. The upper limit is n minus 1. Now expand this. X of n e to the minus j 2 pi by capital N kn times e to the minus j 2 pi by n, and then n times capital N, and this n and that n will get cancelled. So you left with the e to the minus j 2 pi by n. What is this value? This value is always equal to 1. Why? The small n is an integer. Integer times 2 pi is always 2 pi, that is 0. E to the 0 is cos 0 plus j times sin 0. So this value is always 1. So again you will end up with x of n e to the minus j 2 pi kn divided by capital N, where n is equal to 0 to n minus 1. This is once again x of k. So here x of k is periodic with a period of capital N. X of k, previously we stated that e to the x of e to the j omega is periodic with period 2 pi, but this x of k is periodic with the period how much? Capital N. In fact, this is expected because, as I said, x of e to the j omega is periodic with the period 2 pi, and what you have done is the interval 2 pi, we have broken up into n equal intervals, and therefore x of k, capital X of k, should repeat after capital N number of samples. But what is surprising is that if you find out x of n from x of k using Dft, then x of n is also periodic. That is surprising. Originally x of n is a finite length sequence, right? So how do you find out x of n? X of n is equal to 1 over n summation of capital X of k e to the plus j 2 pi kn divided by capital N, where k goes from 0 to capital N minus 1. Now this x of n is also periodic from, if you find out from x of k. Okay, again here you replace n by n plus capital N. It does not change. Okay, so this will be equal to x of n plus capital N, right? So it does not change. So once you find out x of n from x of capital X of k, then x of n is also periodic. The beauty is originally it wasn't periodic. Okay, we started with a finite length of x of n. Whenever you have a finite length, then you cannot say it is periodic, right? So therefore which does not repeat. That is, x of n exists, we assumed, right? What did we assume? We assumed it exists only from 0 to n minus 1. But if you carry out the computation, if you continue to carry out, it will exist beyond n minus 1, capital N minus 1 also, and also in the left hand side. So this is an advantage as well as a disadvantage. Disadvantage is it changed the character of x of n. It made it periodic. Originally it was not periodic, but now it made it periodic. But if you confine your attention to 0 to n minus 1, then this leads to no aliasing. Okay, it leads to no distortion. So if you move your vision beyond this 0 to capital N minus 1 range, then you will end up in a trouble. Therefore, it is important that in DFT, our range of vision, whether in the frequency domain or in the time domain, must be from 0 to capital N minus 1. We can't go beyond that. So, DFT, the range of vision is 0 to capital N minus 1. So, this is important point one must remember. So, whatever operation you do on DFT or the sequence x of n, like you can delay or you can multiply, right? These are the operations that we generally do, right? Multiplication or convolution, whatever you do, we cannot go beyond 0 to capital N minus 1. We can't go below 0 also. Okay, you must not go below 0 and you must not go beyond n minus 1. We must confine ourselves to this limit 0 to capital N minus 1. It is a very important thing which we will come up in a few seconds. And now the one more point I would like to stress here, the inverse formula. What is the inverse formula? IDFT. Inverse formula, x of n is equal to 1 over n summation of capital X of small k e to the plus j2 pi by capital N and kn, where k is equal to 0 to n minus 1 finite summation, and here the running variable is 0, 1, 2 up to, because we need to find out n number of points, right? X of small x of 0, small x of 1, like that. And this is my inverse DFT formula, and this formula can be very easily proved. So, how do you prove this? The proof is very simple. Okay, and here let me indicate the proof. I will outline the proof. Okay, so I will leave the algebra to you. Now this is going to be 1 by capital N summation of x of capital K, and this is, let me denote in the short form notation, Wn minus Kn. Okay, the trick is the same. I mean, in whether in Laplace transform or continuous time Fourier transform or discrete time Fourier transform, the trick is the same. What you do is you replace this x of k by its value in terms of the definition. We know the definition for x of k. So, we write this as follows: 1 over n summation of, here k is equal to 0 to capital N minus 1, 0 to n minus 1, x of k is, what is the definition? Summation of n is equal to 0 to n minus 1, x of n e to the minus j omega n. Do you remember this? I am sorry, minus j, instead of omega we replace by 2 pi by capital N and kn, and already I have this one more guy, w n and minus kn, and here also n and here also n. So, then there will be summation, there will be some confusions. Okay. So, to avoid the confusion we need to change it. Let me replace this n by L, okay, two dummy variables. So, therefore, this n is replaced by L. So, 1 over n, k is equal to 0 to n minus 1, summation of L equal to 0 to capital N minus 1, and this n also replaced by L, x of L e to the, and this one you write in the compact form, w n minus kl, sorry, plus kl times w suffix n minus kn. Okay, now these two summations are independent of each other, and therefore we can interchange these two summations. Okay, you will get the following: 1 over n summation of, one second. Okay, it's okay, no need to, let me write as it is. Yeah, L is equal to 0 to n minus 1, summation of k is equal to 0 to n minus 1, x of L. I can bring this x of L here once I interchange the summation. So, L is equal to 0, x of L summation k is equal to 0 to n minus 1. You combine these two guys, Wn, and the power is, I can write k times L minus n. Okay, combine these two and sum up over k because both contain k. If you take the interpretation of this Wn as e to the minus j 2 pi by capital N and then k times L minus n. Okay, you will simply see very simply that it is equal to, this whole thing is equal to n if L is equal to n. It's very easy to show that. If L is equal to n, then only you will get this value capital N, or this is equal to 0 otherwise. Okay, the whole summation will simplify to n only when L is equal to small n, otherwise it gives the contribution of 0. Okay, so it exists only in one value, and in this also only L is equal to n, and out of the, in this summation, out of capital N capital N number of points, it gives only one non-zero value, that is L is equal to n. Therefore 1 over n, then this is x of n, and this summation is going to be capital N. So n and n will get cancelled, so this is x of n. The left hand side we started with the x of n, and the right hand side also we have x of n. This you can easily prove it. Okay, how? Let's say summation of Wn k times L minus n, k is equal to 0 to n minus 1. Now summation of e to the j minus j 2 pi by capital N times k times L minus n. Now this L minus n must be an integer. Do you agree? L minus n must be an integer, right? So integer times, and k is also an integer. So integer times integer, you will get again integer, and you are multiplying the integer by 2 pi. So by finite sum formula, this is finite sum formula, k is equal to 0 to n minus 1. So this must be equal to 1 minus e to the minus j 2 pi by capital N times L minus small n, and times k. This is by formula I am writing, divided by 1 minus e to the minus j 2 pi by capital N times L minus n. In case if you have like this, let us say a power n, where n is equal to, sorry, let me put a power k, where k is equal to 0 to n minus 1, then this is 1 minus a power capital N divided by 1 minus a. This is the finite sum formula, recall. That same formula I am writing here. Now look at this expression. In this expression, this n and that n you can cancel. 1 minus e to the minus j 2 pi times L minus n. Now if L is different and n is different, if L is not equal to n, then what is going to happen in the numerator? If they are not equal, then the numerator I will get a 0, and the denominator I will get some non-zero value. Denominator also I will get 0 value. No, it may not equal to 0. The denominator is not equal to 0, but in the numerator I will get some other, in the numerator I will get 0. Therefore, this summation leads to 0 if L is not equal to n. In case if L is equal to n, then what is going to happen? Then the numerator will be 0 and denominator also will be 0. Okay, in that case you apply L'Hospital rule and you can find out the value. Okay, then you apply L'Hospital rule and then you find out which is equal to n. If L is equal to n, and this is equal to 0 if L is not equal to n. Therefore, in this summation, the second summation leads to n, capital N, if small l is equal to small n. Therefore, the second summation also, out of n number of terms, only one term is giving contribution, that is when small l is equal to n. So you have x of 0, x of 1, x of 2 like that, but when L takes the small n value, then it is non-zero. That is why we put here. That's how the proof goes. Okay, what is there in the left hand side in this proof? X of n. So x of n is equal to x of n. That's all. Okay, so x of n is equal to 1 second, what is there? 1 over n yeah, I started with this. Okay, the proof is over. Okay, so we have proved. Okay, this is the outline of the proof. You can carry out the algebra. Okay, the only point to notice is this substitution. The only point you should notice one is this one. Substitute Wn is equal to e to the minus j2 pi by capital N and carry out the summation, and you will get this result. Okay, so this is the proof of the inversion formula. Okay, since you have this n times, n is additional n is coming, so you can write the left hand side is equal to this n, and that n will get cancelled, and the left hand side is equal to the right hand side. So the proof is very straightforward. Okay, so let me stop at this point. Thank you very much. In the next class we will work out some problems.